The traditional generators on coal and gas you can control, and they follow the load. But the new sources like wind and solar, they are variable, and that means you don't know always when you have the power supply. And that means that you have to find solutions for that so that the load can be supplied in a secure way. The other is that I can say the capacity factor of a equipment. For example, a load, the maximum load is 18 gigawatt in the Netherlands, and you have 100 terawatt hours of energy supply. That means that about 6,000 hours, the maximum load can be supplied. But if you have solar PV, only 1,200 hours of maximum load can be supplied. That means there's a big gap, and that has to be filled in one way or the other. So a mix of energy is very important. And the third one is that transporting energy, if you have continuous energy flow, you have a certain amount of grid, for example, during 6,000 hours. If you have only 1,200 hours of electricity production, then you need more grid, 5 times more grid. And the challenge is for system operators to really avoid to have huge investments 5 times but less. Yeah, you need really new solutions and say smart solutions, intelligent solutions. And that means that not only wind and solar you need, but also demand-side response. How do you use the flexibility of demand, or batteries? But the combination of these solutions, you have to perform a load flow, for example, and find the right mix. And you have to find the right automation solutions to really make it work. So yes, it's possible, but we have to do other things than we are used today. We need education and research. That's the starting point, I think, as professor. Laboratories are important if we design solutions, and before you can use it as an operator, the system operators, then they must be sure that it's working. So in a laboratory you can test certain solutions in real circumstances. And in the laboratory you test not only intelligence but also materials and new power electronic solutions and electrical vehicles, how to charge in a smart way. All these mix of solutions you can test in a laboratory to test is it really viable in the practice. And here we are in the control room, and here everything comes in. At the end, all solutions but also all not solved challenges comes in the control room, and they have to act all the time. And today the operators work with many solutions in the sense of technologies, but in future more automation, they will work with more subsystems. So from an operator to operate all details, they change over to a supervisor of intelligent solutions. And to test those intelligent solutions, we do that, for example, in the RTDS lab, and we will go to the RTDS lab to see more of that. We are now in the RTDS room, in the RTDS lab. RTDS means real-time digital simulation. That's all about intelligence and a very fast way of intelligence. Here we simulate the grids, and especially the dynamics of the grids. We can simulate, for example, short circuits and high voltages, and what we really simulate is the dynamic behavior of the grid, not a load flow where you calculate during 1 year, but here you calculate during some seconds. And for example, when you have a short circuit, in 150 milliseconds, a circuit breaker disrupts this short circuit. And then the grid behaves in a very fast way, transients we call that. And that's what we here simulate. Why is this then a real time? you can connect real equipment to this computer system so that you can test real, for example, control units for the HVDC converters or protection relays. So in some milliseconds many things happen, and the real voltage and the real current are on the relay. And that's that you need to bring theory in practice. Depends on where you are. For example, in the European grid, all grids are connected to each other. One big system with one frequency. But if you take an island like UK or Ireland, there you have a limited number of production units, a limited number of load, and the frequency can be unstable if you have too many power electronics connected, solar PV and wind. For example, normally you have the traditional generators with a mass, rotating mass, and that we call inertia. But if you have more sustainable sources, you have less traditional equipment. That means you have less inertia. So you can have solar and wind connected to such an island. For example, UK, 40 or 50%. We calculated that in the European project Migrate. And that's possible with the traditional grid following control. If you have the advanced grid forming control, you can go further, up to 70%, and in future even more, but for that research is necessary. So it depends on where you are and what kind of solutions there are available.